So today we're going to look at kind of what else we can do with series. And then I was about to say Monday, but our class is Tuesday, Thursday. So on Tuesday, we'll talk about the next test. So that's kind of coming, it's coming a week from Tuesday, right? So it's not next week, the following week. So we'll talk about that. So, we're going to start then with section, green. Must have been using green last time I wrote here. So we're going to start with section 11.8, which is power series. And the idea of power series is we're going to look at essentially what are infinite polynomials, right? So if you think about, I can put the 11.8 homework up, and I know I'm behind on grading homework. I just am. Like, there's not really a great excuse for it. It's just, I underestimated how much time everything would take to do when you're teaching completely remotely, right? So there are things that, like, generally I just do and they're real quick to do that in the remote environment just are not quick anymore to do. And I did not realize that. I know you guys might be like, really, Dr. Gorman? Like, we're in the third semester teaching online. But the thing is you guys are actually my first semester actually teaching remotely online, because all of last spring and this past fall, I was on partial leave. And so I only had kind of 2 classes, and they were one that I've been managing online for a long time. So I completely was like, oh yeah, I know what's going on. So you guys are the first time that I've been, so the semester's super hard. So, what I actually was going to do with the remainder of the chapter 11 homework, and I was going to talk about this at the end of class, so I'll say it again at the end in case anybody comes in late, but, I wasn't going to make you turn in the remaining sections on chapter, 11. I was going to put the homework up and I'll put the solutions up because I have all them, like the homework and the solutions, but you don't actually have to like turn it in, but you want to try it, right? Because this type of stuff is going to be on the test. But hopefully by now, like, you kind of know the power of, trying the homework, right? And seeing what happens, as opposed to just being like, oh, I don't need to do homework. But I kind of was going to trust you guys for the rest of the semester to be like, okay, like, I understand I should try homework problems. I understand I should see what they are, but I was just going to put up the homework and put up the solutions, and you don't have to upload anything or do anything to get the solutions. You can just have the homework and the solutions right away. So that was kind of my game plan for the homework, actually, for the rest of the semester. So, there's not actually like a due date for the homework, if that makes sense. And I do apologize, because I really thought at the beginning of the semester it would be like, oh, you turn in homework and then boom, I like right away like have it graded and I have the videos you guys are asking for, like, of problems, and it just hasn't worked that way this semester. So like I said, you guys are kind of my guinea pigs in terms of like my first web remote class. You guys, and I have a 127 class this semester, but yeah. So it's been a year, right? So, like I said, this is my first semester back teaching full time, in a year. So it's a little rough to jump into being completely remote. Questions on any of that? No. So the 11.6 and the 11.7, so what's up there now that has due dates, those guys are still due. And then I'll put all the rest of the homeworks up, and I'll just put the homework solutions. So you don't have to, like, you won't see like upload for this, or then do the self-assessment. I should say, if there are still problems that you're like, hey, I really don't understand this problem from your solution, then definitely, like, you guys could either ask me in class or send me an email, and I will still, like, I'll either go over it in class or I'll make a video for it. But this way it kind of makes it a little bit more immediate. So if there's something I did that you guys didn't understand, like, definitely, like, reach out so that I can kind of do it right away, so that, and if you send it to me in an email, it'll get done faster than waiting for me to go in to grade it, to look at what problems you guys have. And I will still make the videos for the ones from chapter 11 for the series and sequences, ones that you guys have asked for before the test. I will definitely get that done either this weekend or next week. So they'll be up for you guys to study from. So any of the problems that you asked for on those problems, I will get done for you. But then from that point forward, so after the stuff that's due on Monday, if you're doing a homework and you don't understand my solutions to it, then just either send me an email or ask about it at the beginning of class. So, other questions? No. Okay. So, back to power series. So power series is basically a way to extend polynomials, right? So all the polynomials we've worked with before have been finite, right? So, like, when we think of things that are polynomials, we think of things like maybe like x cubed plus 5x squared plus, 2, right? Or x to the 11th minus 7x to the 9th plus an x to the 8th minus, 13x to the 5th plus 2x, right? So things like this are polynomials, right? So I think we probably generally know what a polynomial is. A power series is essentially like an infinite polynomial. So a power series is, and so this is not the I'm going to write the formal definition of a power series in a minute. This is kind of like the informal definition of a power series. So a power series is a sum that represents an quote unquote infinite polynomial. Right. So the formal definition is a power series about x equals a is the summation n equals 0 to infinity of c sub n x minus a to the n. And so what this would look like is basically you'd have like the term C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed plus ... right? So you have, basically you have some value that you're centering your polynomial around. That's this a value. So up here, right, these polynomials that I wrote here, these are centered around 0, right? There's nothing subtracting off of the x. But having something centered around something is not unusual. Like, we have actually seen it before. If you've done, think about when you've done problems where you've completed the square, you might end up with something that looks like, x minus 5 squared plus 2. That's a polynomial as well, right? It's just a different way of writing the polynomial. And so in this case, it would be centered around 5 because that's what's being subtracted off by the x. A is what's called the center. So A is called the center. And C sub I are constants. Right? So the the C's in this problem here, like C0, C1, C2, C3, they represent these numbers that are like in front of the X, right? So in this case, when you're centered around 0, these are representing the numbers in front of the X. So like in front of here is a positive 1, right? A negative 7, a positive 2, a negative 13. So basically you have this polynomial and it goes on forever. And one of the things that we are going to look at is that geometric series give these power series. So some geometric series, or not some, all geometric series can be thought of as these infinite polynomials. And sometimes you can take a geometric series and you can make it approximate a function. So the whole idea here is big picture idea. And so let me kind of write it down. So the big picture idea that we're kind of what we're going to be working towards in the next couple sections. So the big picture is we want to represent a function f of x. And so things like maybe like the function 1 over x, or the function e to the x, or the function sine x, right? So different functions that we've worked with. And instead of thinking of the sine function as sine x, we actually want to think of it as an infinite polynomial. So we want to represent some function f of x as an infinite polynomial. So that's the goal, okay? Now you might go, well, that's kind of a weird goal. Why would I want to take something like sine x and represent it as some infinite polynomial? And so there's a couple reasons. One of the reasons is because it is easier to do some mathematics to polynomials than it is to do it to other functions, right? So if you think about it, we've memorized all these derivatives and integrals, but taking the derivative or integral of a polynomial, right? So taking the derivative or integral of, one of these two polynomials is fairly straightforward. But a lot of other functions, it's not as straightforward to take a derivative or an integral, right? That's why we had all those different techniques of integration, right? You have sine functions. You have things with sines in them, or things with sines and cosines mixed together and stuff like that. And all of a sudden you need some like kind of fancy stuff to be able to take the integrals of it, right? We had functions where we had to use trig substitution and all of these kind of crazy things to integrate them. But polynomials are easy to integrate. And so the idea is if I can take a function and I can represent it as a polynomial, then I could actually integrate it or take the derivative of it easier. And you might go, okay, well, why would I want to do that? And so the reason is why you want to do that is because if you think about nowadays, we have so many different like calculators, apps, websites, all these different things available to us that will do calculations for us, okay? When your calculator does a calculation to find an integral between 2 points, it is not doing in the background trig substitution. It's not doing those types of things. Calculators are programmed so that they have series in them, and they make it out to a certain, they kind of cut off the series to say, well, in a calculator, I really only need to be accurate to like 10 decimal places. So as long as my answers work out to the 10th decimal place, it doesn't really matter what happens at the end. So they can kind of shortcut things, and that's how they get some things done faster, by doing these series and sequences. Series. So basically, all of this is to say that series work in the background of a lot of applications. It's easier to take derivatives of polynomials. It's easier to integrate polynomials. It's easier to do calculations with polynomials. So therefore, if we could take functions and we could represent them as polynomials, it's going to make our lives easier. So that's kind of why we do a lot of the series and sequence and stuff. Unfortunately, in Calc 2, you do not see the superpower of series. It's not until you were to get to higher level mathematics, so there's a whole area of mathematics called either Advanced Calculus or Introduction to Analysis, depending where, what school you're at. They're called one of two different things. But in those courses, you actually are proving why you can do calculus. And at the basis of all of calculus are operations on infinite series. And so that's why they're super important. Here, we're kind of like touching the surface of series. So just to kind of put that out there. All right. So that was a lot of rambling. And so let me show you some series and some ways that we can kind of represent them and see what happens with them with polynomials. Okay. Questions, I should say. Questions before I do any of that. I know I was like rambling I can see the timer, right? I've been rambling for like 15 minutes on this topic, so. No. Okay. Okay, so let's look at, the series n equals 0 to infinity of x to the n. Okay, so if I begin to plug in values to see what happens to this, right? So when n is 0, we're going to have x to the 0. When n is 1, we're going to have x to the first. When n is 2, we're going to have x to the second, x to the third, x to the fourth, plus x to the fifth, plus dot, 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 dot. So we have this infinite polynomial. Remember, x to the 0 is just 1, right? So we really have 1 plus x squared, plus x cubed, plus x to the fourth, plus x to the fifth, plus dot, 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 dot. Okay, so x could be any number, right? X could be 5. X could be a half. So x can be any number. So, if x is equal to 5, like I said, this is a summation n equals 0 to infinity of 5 to the n. If x is equal to a half, this is a summation n equals 0 to infinity of 1/2 to the n. So these functions here, 5 to the n, 1/2 to the n, what kind of series do they look like? Yeah, so they look like a geometric series, right? So the summation n equals 0 to infinity. So I should say, it's not just that they look like a geometric series, they are a geometric series. So the summation n equals 0 to infinity of x to the n is a geometric series with r being equal to x. When did a geometric series converge? So do we remember when a geometric series converged? Yeah, so geometric series converged if the absolute value of r was less than 1. Okay, so a geometric series converges when the absolute value of r is less than 1. So, and I should say, anybody remember, it's been a while since we've done them, but does anybody remember how you found the sum of a geometric series? So, and remember, we can only do it if it converged. And when the geometric series converges, right, the sum was equal to, okay, a over 1 minus a. And remember, I wrote it a slightly different as just the first term over 1 minus r, right? So that is the, that's the sum, right? So, oh, yeah, a over 1 minus r, yeah. Okay, so back to our summation x to the n, right? So the sum, n equals 0 to infinity, of x to the n will converge when the absolute value of x is less than 1, right? Because x is the same as my r. And the summation n equals 0 to infinity of x to the n will end up being, so on the bottom you have 1 minus r, so that would be 1 minus x. And the first term, so remember the first term just says take whatever this n value is and plug it in. So it's going to be x to the 0. So this would be 1 over 1 minus x. So what that all means, right? Because you might be going, okay, like I get it, like whatever, or I don't get this. What this is saying is, this is saying that 1 over 1 minus x is the same as the infinite sum from n equals 0 to infinity of x to the n. So it is the same as 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus ... Go on forever, right? So the function 1 over 1 minus x is the same as the function, as the same as the infinite polynomial 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. So that is what's going on there. That's kind of cool, right? Maybe. Yeah. So the idea is that we can determine, you have a function and you can make the function into a series. And it works for other functions too, right? So I could do the same deal anytime I have a function, or anytime I have a series that is geometric, right? Because remember, geometric series are the ones that we can find the sum for. So if you can take your series and somehow turn it into a geometric series, then you can figure out, well, when would it converge? And then at the time when it converges, right, this has to happen. So we should be a little careful. This 1 over 1 minus x is equal to the sum, but only when the absolute value of x is less than 1, right? Because that's the only time it converges. So it's not equal to this infinite polynomial all the time, right? So, but only when x is, the absolute value of x is less than 1. So it does have its limitations. Questions? We're going to look at another one here, one that's slightly more complicated. Right, so it converges. So we're building up to kind of what we're going to be doing here on the homework in a minute. And one of the first things we're going to be doing on the homework is we're basically going to be finding, the values of x that make the series converge. So that's kind of going to be the first thing that we do. And so, yeah, and this, to answer the question, so it converges. Yeah, so 1 over 1 minus x converges to, it's the same as this infinite polynomial, but only when the absolute value of x is less than 1. No problem. Okay, so let's look at another one. So we have the summation n equals 1 to infinity of 1 over 3 to the n times x minus 1 to the nth power. So again, this is some polynomial, right? If I begin to plug stuff in, right, you'd have 1/3 to the first times x minus 1 to the first plus we'd have 1 over 3 squared times x minus 1 squared plus 1 over 3 cubed times x minus, x minus 1 cubed plus dot, 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 right? It would keep going like that. So again, right, this is a geometric series because, so this is geometric, and you might go, really? But we have to work a little bit to make this look like a geometric series. So we have to say, okay, n is equal to 1 to infinity. I could rewrite this as x minus 1 over 3 all to the nth power. Are we okay with how I rewrote that? Like how I got that? Does anybody need me to, I should say, does anybody need me to explain where that came from? It's okay if you do. I just want to explain it before we go on to to using it. No? Okay. So in terms of a geometric series, right, all of this stuff here is my R. And so the first thing we're going to do is we're going to figure out where it converges. So it converges when, so remember the absolute value of R is less than 1. So in our case, the absolute value of x minus 1 over 3 is less than 1. So if I multiply the 3 up, right, because you can think of this is really the absolute value of x minus 1 divided by the absolute value of 3. And the absolute value of 3 is just 3. So this is the absolute value of x minus 1 divided by 3 less than 1. So the absolute value of x minus 1 is less than 3. And you could solve that, right? So minus 3 less than x minus 1 less than 3. Add 1 to everything. So this is going to converge for x values that are between -2 and 4. Okay, so we're going to figure out what the series is going to be equal to some function, but it's only going to be equal to that function between when x is between -2 and 4. And so the sum, n equals 1 to infinity of x minus 1 over 3 to the n is going to be equal to, so again, the first term, so x minus 1 over 3 to the first power divided by 1 minus x minus 1 over 3, right? 1 minus r. And if I multiply the top and bottom by 3, this is going to end up being x minus 1 on the top and 3 minus the quantity x minus 1 on the bottom, or x minus 1 on top, 3 minus x plus 1, so x minus 1 over 4 minus x. So that series, right, the series we started with, is equal to this function, x minus 1 divided by 4 minus x, anytime x is between -2 and 4, right? X equals 5, not going to work. But between -1 or -2 and 4, then it works. Questions? No. Sure. So, so you're okay with this, how I got from this step to this step? Okay. So how I got from this step to the arrow is I multiplied both sides by 3. So times 3 times 3, right? So the 3's would cancel on the left-hand side, and that's how I got the absolute value of x minus 1. And on the right-hand side, we are 1 times 3 is 3. So that's how I got x minus 1 is less than 3. And then we're trying to solve an absolute value. So I think of absolute value in terms of distance, right? So the absolute value is talking about distance from 0, right? So if you don't worry about what's inside here, but it's just saying the absolute value of a bunch of stuff is less than 3. It's saying that all this stuff can only be at most a distance away from it. It can only be at most 3 away from 0. So I could go 3 this direction and get to positive 3, or I could go 3 this direction and get to minus 3, right? So all of that stuff in the middle, the x minus 1, has to be sandwiched between minus 3 and positive 3, right? Because basically I'm allowed to go kind of backwards to minus 3 or forwards to positive 3. Does that make sense? And then all I did was solve, right? So from here down, I added 1 to every piece, right? So add 1 to the middle, I'm going to end up with just x. Add 1 to this side, add 1 to this side. So it goes back to solving absolute value inequalities, which it's probably been a while since people have done, right? Because we do them all the way back in Math 95. So it's a skill you don't always use a ton, but we're going to use it a ton. Other questions? No? Okay, so the problems I've done so far, I've kind of really pushed them into being a geometric series, okay? And so the idea is that you actually can talk about convergence of series that are a little bit more broad, okay? So we need to write down the formal theorem part, and then we'll actually put it into practice, and we'll talk about, okay, what are we actually doing? And then that is what, like, we're doing in this section, okay? So we haven't really gotten to the meat of this section in terms of what exactly it is we're going to be doing. But we need some theorems to be able to do that. And so these are ones we actually need, which is slightly unfortunate that we have to, like, write these big, long math theorems, but we do. So the convergence theorem for power series. Okay, so if the summation n equals 0 to infinity of a sub n x to the n converges for x equal to c with c not equal to 0, right? So basically we're saying I have a power series and it converges for some value c. Then it converges for all x, absolute value of x, that is less than the absolute value of c. And if it diverges for x equal to d, then it diverges for all absolute value of x greater than absolute value of d. Okay, so what's going on here is basically we're expanding the definition a little bit of when things are going to converge. So we're using the fact that in general, if I know something converges and I can get it's kind of like pulling in the comparison test. So if I know a series converges and I have a series that's smaller than it coming in underneath it, then I can say, oh, the smaller series also converges. If I have a series that diverges and then I happen to have a series that's bigger than that, I'm going to be able to say, oh, the series, since this one diverged, I know this one is bigger, so it's also going to diverge. So we're basically just expanding a little bit the rules for converging or diverging. Using from what we just did, where we started with the geometric series, we're just kind of tweaking it a little bit. Okay, then to this theorem, so in mathematics, right, so theorems are kind of like big picture items, and then there's things called corollaries. And so corollaries are basically kind of like, they're very closely related to a theorem, but they usually have like a little bit of a tweak to them. So there's a corollary to this theorem. And the corollary to this theorem says the convergence of the summation c sub n x minus a to the n, so that's that power series we started with, is described by one of the following. So the first thing here is I'm going to kind of put in parentheses what it's kind of called. So the first thing is basically called, well, no, maybe I won't do that. We'll just write it. So the first one says there is a positive number R, capital R, such that when the absolute value of, x minus a is greater than R, the series diverges, and when the absolute value of x minus a is less than R, it converges. Absolutely. Right, so we talked about last class converging absolutely, converging conditionally, or diverging. So basically we're saying one of the things that could happen is that there is some number R where we're basically saying as long as the absolute value of x minus a is less than R, it will converge absolutely. At the endpoints, x equals a minus R and x equals a plus R, the series may converge or diverge. So x equals a minus R and x equals a plus R, those come from actually solving this inequality here. So those are actually the endpoints where the absolute value of x minus a is actually equal to R. So basically we end up with an interval, like we did in that last example. We had an interval, and then those endpoints of that interval. So in the middle of the interval, the series is going to converge absolutely, but at the endpoints, the series might converge or diverge, which means that it's either going to converge, that it might converge conditionally on those endpoints. So that's one thing that could happen. A second thing that could happen is that the series converges absolutely for every x value. When this happens, we say that R is equal to infinity. So the radius is kind of R has a name. R is called the radius of convergence, and so that radius is actually infinite because it converges all the time. Or 3, the series diverges everywhere except x equals a. And here we say that R is equal to 0. When x is equal to a, you just have a big sum of 0, right? So you just are adding 0 plus 0 plus 0 plus 0, so it's always equal to 0. So it's kind of like this non-interesting case. And R is called the radius of convergence. Of the power series. And absolute value of x minus a less than r is the interval of convergence of the power series. Okay, so that was a lot, right? It's a lot of words. I mean, we're like 47 minutes into class, and I still haven't even really shown you what we're doing with problems, right? So I get that it's a lot, right? Questions. I know you guys might be thinking, I don't even know what to ask you a question about because I have no idea what we're doing. And that's okay. If you feel in that boat, hang in here, because in a minute, I think it's going to get clearer. Yeah. And it is easier than it all sounds. So basically what we're going to be doing is we're going to be given a power series, and we are going to want to find the interval and the radius of convergence. Okay. So just like in my beginning examples, like I showed you how, this series becomes this function, and it becomes this function when, when x was, the one example I had, when x was between -2 and 4, right? So this series is this function in this interval. So that interval is basically what we're looking for. So we're looking for that interval and that radius. So our goal is going to be, given a power series, find the interval and radius of convergence. And how we're going to do that is, okay, so when we started all this, we used the geometric series. And the geometric series is great. However, to use the geometric series, you have to work really hard to get it to look like a geometric series, okay? So the geometric series was one of the ones where it converged when the absolute value of R was less than 1. Anybody remember any other series where, stuff converged, where we had kind of lists of like when it converged and it had some absolute values in it? Oh, sure, I can go back for a second. Mm-hmm. Okay, so the last test we did definitely had absolute values. But the last test we did, the alternating series test, is pretty specific. It has to be an alternating series. So one that's maybe a little bit more generic that had an absolute value in it, that we looked at absolute values. Yeah, the ratio and the root test. So we are going to actually use the ratio test. And so what we're going to do is we are going to, if you're given a series and you want to find the radius and interval of convergence, we're going to stick that series we're going to use the ratio test to get our interval, and then we're going to have to test the individual endpoints to see what's happening at the ends. So let me know when I can go back to the next page and I'll write that down. And then finally, we'll actually do some concrete examples. Okay. So, given a power series, find the interval and radius of convergence. How are we going to do that? By using the ratio test to get the interval. And then by checking the endpoints. Okay. So, for example, determine the radius and interval of convergence for A. The summation n equals 0 to infinity of x plus 5 to the n. Okay, so remember the ratio test. The ratio test says look at the limit as n approaches infinity of the n plus first, the absolute value of the n plus first term. So that's going to be x plus 5. Everywhere there's an n, I'm going to put an n plus 1 divided by the original thing that was given, the original term. So divide by the nth term, so x plus 5 to the n. Questions? No? Okay. So here, right, these will cancel out. So x plus 5 to the n will cancel out all of these except for 1, right? And just think about it, if it's like as if I had something to the 5th power over something to the 4th power, right? You'd be canceled out and you'd be left with just one of them. So this is equal to the limit as n approaches infinity of the absolute value of x plus 5 So this is going to be, here, if I look at this, there are no more n's left in my problem, right? So if n is going to infinity, it doesn't matter. It's not affecting this. So the actual limit here is just the absolute value of x plus 5. The ratio test converges, right? So when does the ratio test converge? When the limit turns out to be what? Less than 1. So I want this absolute value to be less than 1. So we're talking about x plus 5 has to be sandwiched between 1 and negative 1. Or if I subtract 5 from everything, it's between negative 6 and negative 4. Questions? No, we're not exactly done yet, right? So I'm kind of done. I have the basis for my interval. I don't completely have the interval yet, right? So I need to check the endpoints, right? So my endpoints are these two things. So x equals -6 and x equals -4. So the first thing is you just do the ratio, or you do the ratio test to see what is your interval of convergence. Now we're going to check the endpoints. So the first endpoint we'll check is when x is equal to -6. So I'm going to go back and I'm going to plug it into my very original series. So we're talking about the summation n equals 0 to infinity of -6 plus 5 to the n. So this is going to be the summation n equals 0 to infinity of -1 to the n. Okay, so think about it. All that happens on the series is it just bounces back and forth, right? It goes +1, -1, +1, -1, +1, -1, +1, -1. So do we think this series is converging? No. And there's a couple things you could do, right? You could use the fact that it's a geometric series and r is not less than 1, right? The absolute value of r is not less than 1, right? So that's another way you can say it if that reasoning it out, like you don't like that here. So you could say, oh, it's geometric, right? R is equal to -1. The absolute value of -1 is not less than 1. So this series diverges. Now we're going to look at x equals -4. So I have the summation n equals 0 to infinity of -4 plus 5 to the n. So we're looking at the summation n equals 0 to infinity of 1 to the n. So 1 to the n is always just going to be 1. So you've got 1, right, plus, so you've got like 1, and then you've got +1, +1, +1, +1, +1. Just keep adding ones. So is this going to converge or diverge? Which one? Yeah, this is going to diverge as well, right? So this diverges. You could do, you could just take the limit of 1 to the n here and see that, yeah, as that it doesn't equal 0, right? So the limit of 1 to the n is not going to end up being equal to 0, so it diverges by the divergence test. Again, it's just 1, so you can kind of think, oh, I'm just adding 1 every single time, so it's not going to converge. So what that means is my interval, I can't put an equal to sign on either one of those sides. If one of these had converged, right? So my next example, you're going to see this. If one of these had ended up converging, we would have stuck an equal to sign on that part of the interval. So the interval of convergence in our case is going to be -6 less than x less than -4. The radius of convergence. So all the radius is asking, right, is basically I have an interval that goes between -6 and -4, right? And so I want to think about smack dab here in the middle, right? So this one's kind of easy to think about, right? Because I've got -6 and -4. So what's smack dab in the middle between -6 and -4? Yeah, -5. And if you think about it, I'm going 1 this direction and 1 this direction, right? So my radius r equals 1. Now, sometimes our intervals are just like not super nice numbers like this, so it's hard to think about it in terms of drawing it. The easiest way to get the interval is to basically take the, you can always add these two, you can always take the difference and divide by 2, right? So if I did, the radius would be -4 minus -6 divided by 2. So the radius is going to end up being 1. So you're basically just finding how long is that interval and then dividing it by 2 to get the radius. So that's generally how I find the radius. I don't actually draw the number line and think, okay, what's the middle and where do I go? But I kind of wanted you guys to see that's really what's happening. And so the way that I do that is just by doing the end, the like rightmost endpoint minus the leftmost endpoint divided by 2. Questions? Okay, so I'm going to show you that. So we're going to do an example here next where the endpoints would converge. Well, at least some of the endpoints. At least one of the endpoints converges. So hold on, see if I answer your question after the next example. Other questions? Okay. Okay, so B, summation n equals 1 to infinity of -1 to the n plus 1, x minus 2 to the n, all over n 2 to the n. Okay, so again, we're trying to find this interval and radius of convergence. So we're going to start with the ratio test. So we're going to look at the limit as n approaches infinity. So I have to take -1 to the n plus 1 plus 1, x minus 2 to the n plus 1 over n plus 1, 2 to the n plus 1, all divided by -1 to the n plus 1, x minus 2 to the n, all over n 2 to the n. And I'm going to rewrite this limit. So we're going to have the limit as n approaches infinity. Okay, now, -1, the -1 to a power, I'm going to ignore that part. And the reason I'm ignoring it is because, remember, we're taking the absolute value. So I don't care whether it turns out to be positive or negative. I'm taking the absolute value. So you can ignore, when you're doing the ratio test, if you have a -1 to a power, you can ignore that part. So left on, I'm going to kind of write this out so we can like cancel things a little nicer. So from the top fraction, I have x minus 2 to the n plus 1 divided by n plus 1, 2 to the n plus 1 times, keep, change, flip. So keep the top fraction, change from division to multiplication, flip the bottom fraction. So we're going to have n 2 to the n over, again, I'm getting rid of that -1 to the n. So I have x minus 2 to the nth power. And then stuff is going to cancel out, right? So the 2 to the n would cancel out the n part here. The x minus 2 to the n is going to cancel out the nth part there. And so we're going to be left with the limit as n approaches infinity of, I have an x minus 2 on the top times n all over n plus 1 times 2. Okay, so I want to find that limit. So a couple things to help me out. One thing is that the x minus 2 part, right, that does not have any n's in it. So the only part that's going to be kind of contributing to my limit is going to be the n part. So I'm going to actually like rewrite this just a little bit. Oh, whoops. I undid the draw with pencil only. I'm going to rewrite this just a little bit to help us out. So the limit as n approaches infinity, I can rewrite this as x minus 2 times n over n plus 1 times 1/2. So I didn't do anything yet to the problem. I didn't find the limit or anything like that. All I did though was rewrite stuff so that it looks a little cleaner. Is everybody okay with what I did? Does anybody have any questions with what I did so far? Okay, so if we look at these pieces, only this middle piece has n's in it. So that's the only thing. As n goes to infinity, I just have to worry about what happens to that middle piece. Now, you could do L'Hopital's rule on that middle piece, right? Like if I plugged infinity in, I'd end up with infinity over infinity, and then you could do L'Hopital's rule. Or you can kind of just remember they're the same power, right? The highest power on the top is a 1, the highest power on the bottom is a 1. So you would just take the ratio of the coefficients. So this whole piece is just going to go to 1. So in the end, when I take the limit, this is just going to end up being the absolute value of, on the top, I'm just going to have x minus 2, and on the bottom, I'm going to have 2. I see that, I'm going to hope that this example does what I want it to do, because I see now I actually copied it down wrong. So we're going to hope, we're going to cross our fingers and hope it does what I want it to do here in a minute. We'll see. So I have this absolute value, and then remember it's going to converge when n is less than 1. So this needs to be less than 1. So we're trying to solve this. So we're trying to solve the absolute value of x minus 2 over 2 less than 1. So that's going to be the same as saying the absolute value of x minus 2 is less than 2. So x minus 2 less than 2 greater than negative 2. Add 2 to everything, so 0 less than x less than 4. Questions so far? So basically, you use the ratio test to get like your potential, to get the basis, not your potential, the basis of your interval. And now we're going to check those endpoints. So to check our endpoints, so if we check x equals 0, we're going to plug it into our original. So the summation n equals 1 to infinity. Negative 1 to the n plus 1, 0 minus 2 to the n, all over, yeah, this is my problem. This is why I tweaked it. well, I should say, this is why me just doing what I did is bad. Oh, no, it's not. It's fine. I'm thinking it was X. Never mind. Don't listen to me. I mean, listen to me, right? But don't listen to the ramblings I just said. I know. Everybody has off days, right? I'm blaming it on the fact that I didn't go to bed till after 1 o'clock this morning, so. Okay. So, if I work out what this is, right, I end up with summation n equals 1 to infinity. I have -1 to the n plus 1. We have -2 to the n, all over n2 to the n. -2 to the n, I could rewrite as -1 to the n times 2 to the n. Right? Because -2 is just -1 times 2. So I could split it up into -1 to the n times 2 to the n. So if I do that, my 2n's cancel. And this is just the summation n equals 1 to infinity. So it's going to end up being -1 to the, I have n plus 1 plus another n. So n plus 1 plus another n is 2n plus 1 over n. Okay, and so we need to think about, if we think about 2n plus 1 for a minute, 2 times any number will give us an even number, plus 1 more will give us an odd number. So no matter what n is, that top is always just going to be -1. So really, this whole entire thing ends up being the summation n equals 1 to infinity of -1 over n. And so it's really just the harmonic series, right? Our harmonic series is 1 over n. We just slapped a negative in there, in front of it. So this is just the harmonic series, which we know is a p-series, and so it diverges. So on the 0 side, it diverges. Excuse me. So now we have to figure out what happens on the other side. Questions? Okay, because so the two -1s don't turn into a positive because it's not, if the power was the same, if it was strictly -1 to, if this was always a -1 and this was always a -1, then yeah, it would turn into a positive 1. However, the thing is this is n plus 1 and this is n. So like, think about it, if you had, like, say if n is 3, you'd have 3 plus 1, which is 4, times -1 to the third. So that's going to be negative, right? If n was 2, this part is going to be odd, and this part is going to be positive. So basically what's really happening here is one of these pieces, this piece is going to alternate between being positive, negative, and this piece alternates between being positive and negative, but they don't both show up negative at the same time. So it's like this one's positive, this one's negative. Then this one's negative, this one's positive. Then this one's positive, this one's negative. So they're alternating with each other. So every single time, one piece is a positive one and one piece is a negative one. And so when you multiply them together, you end up getting a -1. Does that help? The other way to look at it is to just strictly do the algebra, right, which is what I did here. So I added n plus 1 plus n. So I get 2 times n plus 1. And no matter what number you put in here, this is always odd, right? So like 2 times 7 plus 1 is 14 plus 1 is 15. 2 times 100 is 200 plus 1, 201. So this number here, 2n plus 1, is always an odd number, which makes this always be negative. Other questions? So I basically did one endpoint, right? One of the endpoints, x is equal to 0, it diverges. I need to do the other endpoint, right? So I need to look at when x is equal to 4. So I'm going to slide this up so I can kind of do it on the same page here. But you guys should, still have this. So if x is equal to 4, and I plug that in, we get the summation n equals 1 to infinity of negative 1 to the n plus 1, 4 minus 2 to the n over n 2 to the n. So this is going to be the summation n equals 1 to infinity of negative 1 to the n plus 1, 2 to the n over n 2 to the n. So this case is nicer, right? The 2 to the n's would just cancel each other out. And we're just left with the summation n equals 1 to infinity, negative 1 to the n plus 1 over n. So this is the alternating harmonic series. And so in terms of this, so alternating harmonic series, we looked at this before, so we know that this converges by the alternating series test. So alternating harmonic series, so it converges. If you didn't remember that, all you would have to do is the alternating series test, right? So you have to look at the 1 over n part. 1 over n is positive, 1 over n is decreasing. The limit as n approaches infinity of 1 over n is 0. So because of all that, this converges. So you could go through those steps if you didn't remember that this was the alternating harmonic series. So at x equals 4, it converges. Okay, so we got one that converged. Nice. So what this is saying is, that the interval of convergence is 0 less than x less than or equal to 4. So I can put an equal to sign with the 4. And then to get the radius, we're going to do 4 minus 0 over 2. So that's 4 over 2, or 2. So r is equal to 2. Yep. So if, if it had converged for x equals 0, then it would have just been a less than or equal to under each piece. So each time it converges, then, so every place where it's equal to, then you are saying it, I didn't say it right. Every time the endpoint converges, you put an equal to sign. Right? And technically what we're saying here is the following. Technically what this is saying that we converge absolutely for 0 less than x less than 4. So that comes from up here, right? So whatever you get here, this is where it converges absolutely, right? Converge absolutely. And since negative 4 wasn't present here, right? So, negative 4 wasn't part of this, but negative 4 ends up being in our interval. What that tells us is we converge conditionally at x equals 4. So the interval you get at the beginning, that's always the places it converges absolutely. If the endpoint ends up converging, then we say at the endpoint it converges conditionally. Questions? So these problems are just a little long, right? But the steps are kind of the same for everyone. Use the ratio test to figure out what your interval is, and then test your endpoints and see what happens at the endpoints, and then use your interval to help you find your radius. So, should we do another one? Absolutely. I like it. Yeah. All right. So, C. Summation n equals 1 to infinity of x to the 2n over 2n factorial. So again, we're going to use the ratio test, right? So we're going to look at the limit as n approaches infinity of x to the 2 times n plus 1 over 2 times n plus 1 factorial all over x to the 2n over 2n factorial. And again, I'm going to rewrite it so that I can flip that bottom fraction, and I'll calculate out what those numbers on the top are. So this is going to be the limit as n approaches infinity of the absolute value of x to the 2n plus 2 over 2n plus 2 factorial, right? So I just distributed the 2 in both of those pieces, times 2n factorial divided by x to the 2n. And so if we think about stuff canceling, the x to the 2n is going to cancel the 2n of these. So I'm going to be left with an x squared on the top. 2n plus 2 factorial. So remember what that is. It's 2n plus 2 times 2n plus 1 times 2n factorial. Right? So remember, you keep peeling pieces off. So the 2n factorial pieces are what would cancel. And so in the end, I'm left with the limit as n approaches infinity of the absolute value of x squared over 2n plus 2, 2n plus 1. So questions about how I got that before we actually take that limit? No. Okay. So kind of just like I did in the last problem, I'm going to separate out the pieces here. So the limit as n approaches infinity of, I have the x squared piece, which has nothing to do with the n's. And then essentially I have a 1 over 2n plus 2 times 2n plus 1. And so this whole part is the only part that has the n's. And so if we think about that, what happens to that as n gets really, really big? Yeah, this part goes to 0. So I have x squared times 0. So x squared times 0, the whole entire thing is going to be 0. So that's a little weird, right? Because in the last couple examples, we got our interval, and because we had excuse me, absolute value of something with x, but here I just get 0. But remember, we're always comparing it to 1. So is 0 less than 1? Yeah, so 0 is less than 1 always. Right? That always happens. 0 is always less than 1. So what that means is that it doesn't matter what x is in this problem. This converges no matter what x is. So this converges no matter what x is. Okay, so what does that mean? Well, that means my interval is, I don't care what the x values are. It goes from minus infinity to infinity. I can take every single value of x that I want. And what that means for our radius, right? Because now you're like, well, how do I figure that out? Because I can't really subtract them. So when your interval is from minus infinity to infinity, we just say that our radius is infinite. So, right? Because I'm going out an infinite number in both directions. Questions? No. Okay, so kind of going back to where we started at the beginning of class, right? I said, oh, power series are important because we want to be able to take our functions and represent them. We want to be able to represent functions as series, infinite series, and I kind of sort of talked a little bit about why you wanted to be able to do infinite series. And so the thing is that, so kind of, let me go to the next page here. Okay, so we care about the interval and radius of convergence, or mostly the interval. So we care about the interval of convergence. Because if a series converges, then we can differentiate and integrate the terms of the series. to find derivatives and integrals. Otherwise, if the terms of your series don't differentiate, if the terms otherwise don't, if your series doesn't converge, you can't just take the derivatives of each of the pieces, okay, and get something meaningful. You can take the derivatives of each of the pieces, but it's not going to be the same as taking the derivative of whatever function it represents, right? So the idea is here, and if you think back to integration, right? When we learned integration techniques, we learned techniques that you can only make things convert, like you can only integrate things, certain functions, right? They have to fall into one of the techniques we know. And those techniques were pretty limiting. Like there's a lot of functions that we can't integrate by hand because we don't have a good technique to do it with. However, now if you can, which we're not quite there yet, but we're almost there. If you could so say you want to integrate this function and none of our techniques work. You could take your function, turn it into a series, and then you now have a polynomial, and you could integrate the pieces of the polynomial as long as that series converged, okay? So it's a way to be able to do integration when I don't actually have a technique to integrate the closed form of the function. But I have a technique to integrate this infinite polynomial, right? Integrating polynomial pieces is easy. So that's kind of the power. That's the power of power series, right? Ha ha ha. A little bit of a joke there. Maybe just a little tiny bit. No one's gonna give me a little I need a laughing emoji here on the screen, right? I feel like I need to be on Instagram Live or Facebook Live where people can, flood my little screen with hearts or laughing faces. Yeah, see, it's funny. Come on, right? I'm doing my best here. There we go. All right. I knew I could count on you guys. Okay. So I think there is I don't know how to do the reactions, but there is a way to do it. There we go. See. Oh, there we go. So, all right. So, we have one more chunk of stuff to do. And I originally was going to start it today, but we're not going to make much headway in, the 15 minutes that's left. So why don't we stop there? I will, like I said, I will put up the homework for this section. You don't have to turn it in, but you should try it. Check your answers against my answers. And then I will see you guys next week. And I think we're still probably on track to be able to finish what we're doing with series on Tuesday. I keep wanting to say Monday. I don't know why. But we'll finish that on Tuesday. Questions before we go? Oh, nice. Having an infinity is definitely helpful. All right. So, I will see you all then. No problem. Have a good one. I should get more sleep before Tuesday, so should be a little better.